I'm Fahim Mahmood. Today I'm going to talk about the theory of relativity. Theory of relativity is one of the most famous theories in physics, and it was proposed by Albert Einstein. This theory has two parts, special relativity and general relativity. In this video I'm going to introduce you to both special and general relativity and give you an idea about what this theory is all about. And at the end of this video I'm going to show you a demonstration on general relativity for better understanding, as it is a little bit more complex. Now at first, special relativity. Special relativity applies to only inertial reference frame. Inertial reference frames are the frames which are not accelerating. It is either at rest or moving in a straight path with uniform velocity. It can't go around a circular motion with uniform velocity because even though the magnitude of its velocity remains same, its direction is changing. So it is subjected to an acceleration, and that acceleration is called centripetal acceleration. So it can't go around a circular motion. Now, special relativity is based on two postulates. Number one, all the laws of physics are invariant in an inertial system. If this frame is at rest or moving in a straight path with uniform velocity, then it is an inertial system. If you are inside the system and the system is moving in a straight path with uniform velocity and you are not allowed to look outside, then you won't be able to tell if you are at rest or moving with a uniform velocity. There's no experiment you can do to determine that. Now the second postulate is that the speed of light is same for all observers, regardless of the motion of the source of light. This may seem a little bit unintuitive, but this was proved by an experiment by two persons named Michelson and Morley. In this video, I'm not going to talk about the experiments that they did, but I'm going to show you a similar case. Suppose I'm standing here. You are inside a train which is moving in this direction with speed 50 meters per second relative to me. You are inside the train and you have a ball in your hand. You will say that the ball is at rest relative to you, but I will say that the ball is moving with speed 50 meters per second. Now if you throw the ball in the direction of the motion of the train with velocity 10 meters per second, you will say that the speed of the ball is 10 meters per second in this direction relative to you. But if you ask me what velocity of the ball do I measure, then I will say that the velocity of the ball is 10 plus 50. 10 plus 50 equal to 60 meters per second. This is totally intuitive. But you are in this similar train moving in this direction with speed 50 meters per second. You are inside the train. But instead of having a ball, now you have a torch. You switch on the torch and the light travels in this direction, in the direction of the motion of the train. You will say that the velocity of the light is 3 into 10 to the power 8 meter per second relative to you. The speed of the light is denoted by letter C. But if you ask me what velocity of light do I measure, then I will also say the speed of the light is c equal to 3 into 10 to the power 8 meter per second. I will not say that the speed of the light is c plus 50. I will not say this. And this was proved by Michelson and Morley. Now, in classical physics, we have learned that length, time, mass are absolutes, but according to the theory of relativity, length, time, mass are variables. They can vary. Now I'm going to show you how. First, I'm going to talk about the relativity of length. Suppose I'm standing here. I'm standing in a frame which is at rest. You are also standing in another frame which is at rest relative to me. You have a stick in your hand. Now when you are at rest relative to me, you measure the length of the stick to be 2 meters. At that time I will also measure the length of your stick to be 2 meters when you are at rest relative to me. But when you are moving with the uniform velocity relative to me in this direction, you will measure the length of the stick to be exactly 2 meters. But if you ask me at that time To measure the length of the stick, I will say that I measure the length of the stick to be less than 2 meters. I will say that it measures less than 2 meters. This phenomenon is known as length contraction. Length contraction means a moving object contracts in length in the direction of its motion. Now, relativity of time. Suppose I'm standing here, you are in another frame which is moving relative to me in this direction. We both have a watch. We know that if two clocks are synchronized at time 0 and started at the same moment, the two clocks will remain synchronized for the future times. It means that the rate of ticking of time will be same. Now say you go from this point to this point. Now when you come by my side, then let both of our clocks get synchronized at t equal to 0. Now when you surpass me, both of our clocks starts ticking. After some moments, I say that the time reading in my clock is t, and at that same moment you will say that your time reading is t prime. From our daily experience, we will say that the t is equal to t prime. My time reading is equal to your time reading at the same moment. But this will not happen as you are moving relative to me with a uniform velocity. As you're moving relative to me with uniform velocity, my time reading will be more than your reading. This phenomenon is known as time dilation. Time dilation means a moving clock runs slow. Similarly, there is relativity of mass. Suppose I'm standing in a frame which is at rest. You are also standing in another frame which is moving relative to me with uniform velocity. But when you are at rest relative to me, suppose you measure your mass to be 50 kg. At that time, I will also measure your mass to be 50 kg as you are at rest relative to me. But when you are moving relative to me with uniform velocity, then you will measure your mass with 50 kg. But if you ask me to measure your mass, then I will say that your mass is more than 50 kg as you are moving relative to me. So relativity of mass tells us that a moving object's mass increases. All these phenomena I have shown can be proved that it actually happens by mathematical equations. As I am running out of time in this video, I won't be able to show you all these mathematical equations. So I'm going to now talk about general relativity. Now, suppose this is Earth and this is the Sun. We know that Earth goes around the Sun because there is a gravitational force. Newton said that, but he could not say how this force works between two objects. But Einstein explained why Earth goes around the Sun, how this gravity works. Now there is space around Sun. Due to presence of Sun, which is very massive, the space curves. Now I'm going to show you how. We know space is three-dimensional, but for simplicity let us consider this two-dimensional clock to be space. Now if this is Earth, if I push it on the space, it will go in a straight path. But if there is presence of massive particle at the center, suppose this is the Sun, then the space gets depressed or creates dimples, so it becomes curved. Now if I do the same, it will go around. I will do it again. See, it goes around. There is air resistance and friction here, but in the space there is no friction or resistance, so it keeps on going around the Sun. So I made this demonstration with tablecloth and some clips, but I hope this gives an intuition. Thanks for watching.